Hey guys, this video is about spontaneity and entropy. How spontaneity is determined by this property called entropy. So let's look at what we know so far, thermodynamics-wise, thermochemistry-wise. We know that if a process is exothermic, oftentimes it's spontaneous. For example, the combustion of methane, CH4, combining with O2, is an exothermic process, and this happens spontaneously once we get over the activation barrier, which is another story. Some processes, though, happen spontaneously, even though they're endothermic. A real good example is the dissolution of ammonium chloride in water. This is an endothermic process. Delta H for this reaction is a positive 14.8 kilojoules per mole. We have to put 14.8 kilojoules per mole into that system to get this to dissolve. Where does it come from? Surrounding the water and the environment. Whereas with the combustion of methane, this releases 890.7 kilojoules per mole. So in other words, for an exothermic process, the energy of the products is lower than the energy of the reactants. And a ball will roll downhill if you let it go, because it's in a lower energy state at the bottom of the hill than it is at the top. Has less potential energy. Kind of the same idea here with the methane. The products are at the bottom of the hill, reactants are at the top, and you release that ball just by lighting a match or whatever, and it just rolls right downhill. It's spontaneously. But this is almost like that ball rolling uphill by itself without you even pushing it, right? So what's going on? There has to be something else involved, and that thing, that driving force for spontaneity is called entropy. So entropy, the symbol we use is a capital S. Everybody uses that symbol. And you'll see, if you Google this, you're going to get, you're going to get confused, right? There's a whole lot of people out there defining it different ways. My recommendation is stay away from the people that talk about it in terms of randomness. That's not really a correct way to think about it. Proper way to think about entropy is as a measure of how dispersed the total energy of a system is. How many ways we have of distributing that amount of energy within the system. And here we're talking about mostly kinetic energy. We'll see some other types of energy too, but mostly we're talking kinetic energy. And so in terms of kinetic energy, the types for a molecule, the types of kinetic energy that there are, the places that it can go, the way it can be distributed is through one translation. This just means, zipping through space, right? Or the molecule can vibrate, assuming there's more than one atom in and if it's a molecule, right? And so if we're looking at these two molecules over here, fluorine, which has 2 atoms, and ozone, which has 3. Fluorine can vibrate pretty much just one way, the 2 atoms back and forth, like they're attached with a spring. But ozone has 3 atoms in it. This has all these different ways that it can vibrate and oscillate. It can stretch. Both of the outer atoms can stretch out. They can both push in. One can pull in, one can push out, the other way around, and they can flip up and down, kind of like this over here. That's all vibration. There's different ways, more ways in ozone of distributing the kinetic energy through vibration in ozone than there is with fluorine. They both have the same amount of, same ways of distributing kinetic energy through translation, zipping through space. And in terms of rotation, the fluorine molecule, the only way it looks different is if we rotate it about either of these 2 axes. Do it down here, that we impose the Cartesian coordinate system on the center of the molecule. If we rotate it about the y-axis, and we rotate it about the z-axis, we can, it's rotating. But around the x-axis, it doesn't really change, right? Whereas with ozone, there's different ways of distributing the energy by rotating about all 3 axes. So, point being, there are more ways to distribute the energy in ozone. And we're going to see that come into play in just a minute. But that's what we're talking about when we're talking about dispersing the energy or distributing the energy, entropy. So Boltzmann's definition of entropy is this. This little equation up here, really famous. S, the entropy, is equal to K, which stands for Boltzmann's constant, times the natural log, this is ln, the natural log of omega, where omega is the number of available states to the system. We're going to talk about that in just a minute. Here, let's go back to Boltzmann's constant. Remember, this is the gas constant divided by Avogadro's number. So R, 8.3145 joules per Kelvin mole over Avogadro's number, 6.0221367 times 10 to the 23rd per mole. And at least to 4 sig figs, this ends up being 1.381 times 10 to the minus 23rd joules per Kelvin. So okay, so that's Boltzmann's constant, net number of available states. So first, before we get into this, let's look at what the equation tells us. It says that the entropy of any system is equal to some constant, it's a really small number, but it's not zero, times the natural log of how many available states it has, the number of different ways it has of distributing the energy, the total energy within the system. So the greater omega is, the greater the entropy is. And it's a logarithmic relationship, but you increase the number of ways you can distribute the energy, you increase the entropy of that system. So let's start talking about how we can distribute the energy. Omega, okay, is equal to the number of different places a molecule can be. So now we're talking about translational energy. We're not thinking yet about the rotation or the vibration, really. That depends upon the actual molecule itself. So at this point, we're assuming it's the same molecule, so that's not going to be different. And we're also not looking at where the electrons are for the moment, because again, if we're assuming the same molecule, that's going to be the same for all the molecules. But what is different here, okay, is between these two pictures, is we start out with this barrier, this little purple sliding door in this box. And we have all the molecules in the left, right? So it's a gas. It makes it easier to think about. And the number of available states are omega, and the number of equivalent ways that the energy of this system can be arranged is equal to x, the number of different places a molecule can be raised to the nth power, where n is the number of molecules. Now, we're going to talk about how we can figure out, or think about the number of different places the molecule can be x. But hopefully you can see, at least at this point, when we raise this barrier, each of these molecules has more places that it can be. So x increases. We have the same n, but because x increases, omega increases, and the entropy increases. So the system on the right, again, we're assuming everything else stays the same temperature, all that, same number of molecules, everything. We just increase the volume. There's more, in this case, volume. There's more different, there are more places the same molecules can be on the right-hand side than there are on the left. That means there are more different ways of distributing the energy amongst those molecules on the right, which means the entropy on the right, again, everything else being constant, is greater than the entropy of the system on the left. So let's break that down a little bit further and see how we think about the number of different places the molecule can be, our x, right? So here we're going to make it really simple, okay? We have two molecules, the green molecule and the red molecule, the red pill and the blue pill. And we have a barrier, and so in this system right here, the molecules can be either both in the top, both in the bottom, red in the top, green in the bottom, or green in the top, green in the bottom. We have two different places the molecule can be. X is 2. We have two molecules. The number of particles in the system is 2. So x to the n is 2 squared, which is 4. 1, 2, 3, 4 different ways that the energy can be distributed amongst the particles, the system. Now, okay, so we have x to the n, omega is 4 in this case, right? Really small number. Usually for realistic systems, we're talking astronomical numbers, but that's why the log term is in there, by the way. Now let's open this barrier. Okay, so this dashed line right here, this is our imagination dividing the box into parts. So here we just have two different places. X is 2. When we open the barrier, that same line is there, and we also draw a line down the middle. Now we have 4 different boxes. So our x is 4. N is still 2, so 4 squared is 16. 16 different ways of arranging where those molecules can be. 8 of them are shown here. There are 8 others. These 8 are all with 1 molecule in each box. Green on the left, red on the right top. Green on the left bottom, right on the top, red on the top right. Red on the bottom left, green on the top right, both of them in the bottom, red on the left, green on the right. And then, you can just go through the various permutations. So there are 8 of these. There are also 8 more arrangements where both molecules, 4 of those, both molecules are on the left, just like this, and 4 of them where both molecules are on the right. The mirror image of this. That's a total of 16. So once we open this door, guys, we pull this sliding door out, because we have more ways of distributing the energy. We have more places those molecules can be. X increases. We have omega, the number of states increases, and the entropy increases. Again, we're assuming everything else like temperature stays constant. So, okay, that's enough of that. Now let's start expanding and talking about more realistic systems, larger systems. So in general, the change in entropy, so we've just talked about flat out entropy, not changes. Now we're talking about changes. So when a system undergoes a change in entropy, the change in entropy is just the final entropy minus the initial entropy. But we know entropy is K, L, and omega. So the entropy of the final state is K, L, and omega final minus K, L, and omega initial is the delta S. Just using the properties of logs, we can write this as K, L, and omega final over omega initial. But we know omega is x to the n, so we could write this as K, ln x final to the n over x initial to the n, which is like this whole thing raised to the nth power. Using another property of logs, we can bring that n out front, and we get K, capital N, ln x final over x initial. Number of states in the final system minus the number of states in the initial system. Here, in we're still thinking about those boxes and the sliding door. X is the number of cells, right? Which means that we could write the total volume of their system, capital V, as the volume of one cell times the number of cells, right? So little v times x. Rearranging this, x is just the total volume over the volume of one cell. If we substitute in here, in place of x final, we'll put v final over little v, and x initial, v initial over little v. The little v's cancel because the volume of one cell is the same, right? We define it. So we just get the change in entropy of the system is equal to K, N, which is the number of particles, ln of the final volume minus initial volume. Now, this is assuming temperature stays constant and so on. Now, if we assume it's an ideal gas, so if we're just talking about a gas which we can actually extend to other systems, but we won't have to here. So remember, K, this is Boltzmann's constant. This is R, the gas constant, over Avogadro's number. But the number of particles is just the number of moles times how many particles there are per mole, Avogadro's number. If we substitute in place of N here, we substitute N, the number of moles. That little n means the number of moles times Avogadro's number. And in place of K, we put R over Avogadro's number. Avogadro's number cancels, and we get something that's useful. We actually can use this equation. Change in entropy of a system is equal to N, the number of moles of the gas, times the gas constant, 8.3145 joules per Kelvin mole. That's the value we use. Natural log of the final volume over the initial volume. So this only applies to the isothermal expansion or compression of an ideal gas. So, an ideal gas, and we'll assume that here all the time for this scenario. Isothermal means the temperature doesn't change. So if we look at this, right, if the final volume is smaller than the initial volume, that means it's being compressed. That means that this ratio here is less than 1. The natural log of that will be a negative number. N and R are both positive numbers. So that means if the final volume is less than the initial volume, the entropy of the system decreases. Delta S is negative. And so at the end, we have less entropy than we started with. On the other hand, if the final volume is greater than the initial volume, this is an expansion, it's getting bigger. This ratio is a positive number, delta S is positive, and the entropy of the system is increasing. So let's use this. So we're just going to use that equation we just saw. So the problem is calculate the change in entropy, delta S, of the system when 0.2345 moles of an ideal gas undergoes an isothermal expansion from, so this is the initial volume, 5.712 liters, to, this is the final volume, 6.988 liters. So you're just going to plug into that equation. Go ahead and work it out real quick, guys, and come on back when you get your answers. Welcome back, guys. So there's our equation. N is 0.2345 moles, R is 8.3145 joules per Kelvin mole, final volume is 6.988 liters, initial volume is 5.712 liters. Now notice, it doesn't matter what units the volume's in as long as both the initial and final volume have the same units. It's going to be in bushels, it doesn't matter, you get the same answer. So plugging in N, R, ln V final over V initial, we get positive 0.3931 joules per Kelvin. This is a unit of entropy, joules per Kelvin, or if it's molar entropy, joules per Kelvin mole. So the entropy of the system increases, not by much. A joule is a really small amount of energy, and that many joules per Kelvin is not much, but it's not negative, and it's not zero. So the entropy of the system increased by 0.3931 joules per Kelvin. All right, so now standard entropy. So this is a definition for you guys. The standard entropy of a substance is the entropy that that substance has at exactly 1 atmosphere of pressure. Notice we said nothing about temperature. It's not part of the definition, and when you talk about standard entropies, you have to specify the temperature. A lot of times it's at 25 Celsius, and that's pretty much what we'll do. So at 25 Celsius, because as you change the temperature of a system, we'll see this in a moment, you change the entropy. So the entropy of these substances would be different at a different temperature. But at 25 Celsius, these are the entropies of some substances. And let's look at this for a minute. So let's compare the first two rows. Liquid water and gaseous water. So notice the entropy goes up quite a bit when we go from liquid to a gas of the same substance. This many joules per Kelvin mole to 188.7, right? So that's we'll see across the board. When you go from a liquid to a gas, everything else staying the same, entropy increases. Likewise, with sodium, we go from a solid to a liquid. The entropy goes up, not nearly as much as it does when it goes from a liquid to a gas, but it does go up, and that's also very common. Going from a solid to a liquid, the entropy increases, but it increases dramatically going to a gas. And then comparing like helium and neon, neon has a higher entropy than helium, and we'll see that's because neon has more electrons, basically. We'll talk about that in a minute. Diamond to graphite. So graphite has greater entropy than diamond. Graphite is the standard state for carbon. This is the most stable form because it has the greatest entropy under room temperature and pressure. Oxygen and ozone, so these two molecules, there's more atoms. We saw ozone, it's pictured back when we were comparing it to fluorine down here. It has, all of these are gases. More atoms means more entropy. Ozone, oxygen, and fluorine are pretty close. I mean, that's a pretty close entropy. And then there's gold and liquid and solid, and mercury liquid. So anyways, we're going to look at why all that is in just a minute. But let's first talk about a chemical reaction and the change in entropy for that reaction. So now, so we talk a lot about systems and surroundings, and we saw this back in Chem 101 when we were first introduced to thermochemistry. And here, when we're talking about the system, at this point we're talking about the chemical reaction, and the surroundings will be the rest of the universe. So for our general chemical reaction, the change in entropy of the system or of the reaction, we're going to first write our generic chemical equation, AA plus BB equal to CC plus DD. Now remember, guys, that in this form, the lowercase letters stand for the coefficients in the balanced equation for each of the species, and the capital letters stand for the formulas of each of the species. Right? So capital A might be H2O and little a might be 2 or something like that. So one way to calculate the change in entropy, the standard change in entropy under standard conditions, 1 atmosphere of pressure for a reaction, is just products minus reactants, just like we saw for enthalpy, Hess's law, and all that good stuff back in Chem 101. So it's the entropy of each of the products times their coefficient in the balanced equation. Now this entropy here we're talking about, this is the standard entropy, and that's actually the molar entropy. When you look up the standard entropy of substances in a table, it'll give you units of joules per Kelvin mole, because that's the entropy of 1 mole of that substance at 1 atmosphere pressure. Anyway, products minus reactants, each multiplied by its coefficient from the balanced equation. For example, okay, back when we first started talking about entropy, we looked at the combustion of methane compared to the dissolution of ammonium chloride in water. Now, if we look at the dissolution of ammonium chloride in water, and we look up the standard entropies of each of these substances. Now, these numbers here, guys, first, I do not expect you to know these or even remember them or anything like that. I looked these up in a table, and you'll always be given this stuff or given a table to look it up in. Anyways, if you go and you look up the entropy of the ammonium ion in water, you see it's 112.8 joules per Kelvin mole. Now, different tables will give you slightly different numbers because they're not consistent across the board because factors change, but something like this. And the entropy of the chloride ion in water is 56.5 joules per Kelvin mole. So this is our Cc plus Dd. It ends up, in this case, the C, the A, B, well, the C and the D are both 1, lowercase. There is no B, right? Because A is just the ammonium chloride. Anyway, the entropy, the standard molar entropy of ammonium chloride solid is 94.56 joules per Kelvin mole. Another word, it's another thing to keep in mind. The state really matters. We saw that when I gave you those sample entropies. A solid has a different entropy than a gas of the same substance, for example. And aqueous is definitely of an ion is definitely different than a gaseous ion or the neutral compound. But anyway, when we plug these numbers in, here's the point, guys. The standard change in entropy for this reaction is positive 74.7 joules per Kelvin mole. The entropy increases, and this right here, guys, this is the reason why, at least at room temperature, this process is spontaneous. If hand coolers, right? If you dissolve, if you have some ammonium chloride and you in a pouch inside of some water, you break the pouch, it'll get cold, right? Because it's absorbing this much energy. We didn't get to the energy yet, but the entropy change is this. It happens spontaneously, but it's an endothermic process. I think we saw that was like positive 14.7 kilojoules per mole or something like that. But the reason that it happens is the entropy increases. And we'll get into this even farther, guys, when we see really what has to happen is the entropy of the universe, which we'll get to, has to increase for something to happen spontaneously. So, factors that affect the entropy of a system. So we've brushed on almost all of these already, but here they are. I'm going to list them for you. These are things to think about when trying, because one of the things we do is try to figure out if the entropy of a system is greater than another system, for example. So when we increase the volume of a system, again, everything else staying constant temperature, number of molecules, all that good stuff, because there are more ways of the energy being distributed amongst those molecules can distribute themselves in more places with different arrangements of energy. We have more entropy. So as we increase the volume, everything else being constant, and this is sort of the picture that we're thinking about. We talked about this before, the sliding door here, and then we open it up. Now we have, there's 4 possibilities here. Our x to the n, our omega was 4 here, 16 down here, there's 8 others. So the takeaway from this is increasing the volume, keeping everything else constant, number of energy states, and thus the entropy increases. And vice versa when you decrease the volume. We saw that I could actually do that calculation for an isothermal expansion or contraction of compression of an ideal gas. Delta S equals nR ln V final over V initial. Okay, now temperature of the system. So the thing to think about with this one here, guys, is that, again, everything else is staying constant. Now we're changing the temperature, volume staying the same and all that. As we increase the temperature, okay, there's more, we're thinking kinetic energy here. There's more kinetic energy available. That means there's more ways of distributing that energy. There's more energy states available to that system. So if we start with the system at, say, T1, we have, say, 3 different energy states that we can, 3 different ways we can arrange the energy. Right? As we increase the temperature, that system has more energy. There's more ways of distributing that energy. The total energy will stay the same over here, but there's more ways of spreading it out. So there's more entropy. So we increase the temperature, everything else but temperature staying the same, the entropy increases. And vice versa. If we decrease the temperature, everything else being the same, the entropy decreases. Another thing that can affect the entropy, and by the way, these are not don't all have the same magnitude effect. Some have a larger effect than others. We're just looking at the factors at this point. More complex a molecule is, we saw this before, more modes of vibration and rotation it has, the same degree of translation, right? But more modes of vibration and rotation, the more energy states available to it, more entropy. So we talked about fluorine versus ozone. There's more ways of this molecule distributing the energy, the vibrational energy up here, and more ways of, in ozone, of distributing the rotational energy compared to fluorine. And so more entropy, everything else staying constant, the more complex the molecule. The greater the molar mass. Okay, so now we're talking about pretty much electronic energy, the energy of the electrons in the atom or the molecule. So, and these are, this is back in MO theory, back in Chem 101. You don't have to, we don't have to go into details of this, but this is molecular orbital theory. And the ground state of the hydrogen molecule is sigma 1s2. There are 2 electrons in the lowest energy sigma 1s molecular orbital. And for nitrogen, okay, which has a greater molar mass than hydrogen molecule, its molecular orbital energy diagram looks like this. There's also, remember, there's the sigma 1s and the sigma star 1s down here. They're full. We have the sigma 2s and all these different molecular orbitals. We have more ways, more energy states available. The more electrons there are, the more ways there are of distributing that energy, the more states there are available to it, and the greater its entropy. This is why, when we, back in that table, when we looked at, I think, I gave you examples of entropy, standard entropies. We had, I think, helium and neon. We saw that neon had a greater entropy than helium, both of them being gases. Here's why. Neon has a greater molar mass, which means more electrons, which means more ways of distributing the energy. Now, this effect is not nearly as great as distributing the energy through vibration or rotation, which that, by the way, is not nearly as great as what we're about to look at, going from one phase to the other. This, we saw when we looked at that table of those sample entropies, we saw that when we went from a solid to a liquid, the entropy increased, but not by a lot. And so the reason is, in a solid, the molecules or the particles are fixed relative to each other. They don't have translational degrees of freedom. They can't move around. They can vibrate a little bit. There's electronic, but they can't really move around. Now in a liquid, the particles, remember the picture is in a liquid, the particles, the molecules can all move around. They're sliding over each other, but they're touching each other, right? So they're still attracted to each other. They're still intermolecular forces, but they can move around. So there's more degrees of freedom. They have translational degrees of freedom now, as well as any rotational, vibrational degrees of freedom they might have. So the entropy increases a little bit. But when we go to the gas, now these particles are separated from each other. They're, this isn't a very, pictures not to scale, because remember, in a gas, the particles are very far away from each other compared to their size, right? There's a lot of space between these guys. There's a lot of different ways of distributing the energy because there's a greater volume that they're in. Again, assuming the same temperature, same number of particles. So when we go from a liquid to a gas, we really jump up the entropy quite a bit. So as we go from one phase to another, the entropy changes. Solid goes to liquid, entropy changes some. Liquid to a gas, we really get a big jump in the entropy. So, which is one reason why during a chemical reaction, one way we can determine or predict just by looking at the balanced equation whether or not the entropy will increase, decrease, or stay the same is just by looking at how many gaseous molecules there are on the left and the right of the arrow. If there are more gaseous molecules on the right side of the arrow, and here we're just assuming there's 1 to 8 to 5 to 6, right? Think about moles, if you will. So for example, in this balanced reaction, the combustion of N-pentane, we have 5 plus 6, which is 11 molecules or moles of molecules of gas on the right, whereas on the left, we have 8 oxygens. This is a liquid that doesn't count. So we go from 8 gas particles to 11 gas particles. We have more gas particles on the right than the left. We predict that the entropy increases in this system, and it does. On the other hand, if there are more gas particles on the left than on the right, then the entropy is decreasing as we go from left to right. And if they're the same on both sides, it stays the same. The entropy stays the same. All right, so here we are. The system, the surroundings, and the universe. So the universe is everything. I mean, the universe, right? We're not going to talk about multiple universes here. So the universe we define as being the system that we're interested in plus the surroundings, which is everything else. So the change in entropy of the universe will be equal to the change in entropy of the system plus the change in entropy of the surroundings. Now, okay, we're going to use this guy in just a second. Remember, reaching back into Chem 101, back into thermochemistry, when we talked about enthalpy, we saw that Q, the amount of thermal energy transferred, is equal to the change in enthalpy at constant pressure. Remember, in general, delta H is equal to Q plus W. Here, at constant pressure, there's no PV work, so it's just Q, they're just transferring thermal energy. Okay. So remember, it's keeping stuff at a constant pressure. If the process is exothermic, that means that Q of the system, that means it releases thermal energy. Q of the system is negative. That means that Q of the surroundings is positive. So in an exothermic process, the system, in this case, for us, the chemical reaction, ends up at a lower energy state. And that difference in energy goes into the surroundings, which is why when a match feels hot to us, because that combustion is exothermic. If we were the match, we would feel cold. We're losing energy. For an endothermic process, that means Q of the system is positive and Q of the surroundings is negative. So when we dissolve that ammonium chloride in water, energy went into the system. I think 14.7 kilojoules per mole we saw. And that means where'd it come from? Well, the surroundings, whatever they are. The water, the glass, the air, what have you. Now, back to entropy. If Q increases, if the amount of thermal energy increases, remember, thermal energy is basically kinetic energy. There are more energy states available. We saw this already. Greater temperature means greater kinetic energy, more energy states available. And that means the entropy increases. Now we get to the second law of thermodynamics. Okay, so the first law of thermodynamics basically says that everything wants to be in the lowest energy state that it can be in. But it does not predict spontaneity. It doesn't predict which direction something's going to go spontaneously. So we saw this with our ammonium chloride compared to our combustion of methane in the first few slides. So here's the one statement. There are multiple statements of the second law of thermodynamics. Planck's statement, Carnot's statement. There's many, but think about it this way. It says that for a process to be spontaneous, the entropy of the universe must increase. If the entropy of the universe increases in a spontaneous process, that's what we call, you don't have to really worry about this, but these are the terms. It's what we call an irreversible process. Or the entropy, at least, of the universe must remain the same. Delta S of the universe be 0. That's only for what we call a reversible process. And that's the last we're going to talk about, reversible versus irreversible at this point. But, okay, here's also another statement of the second law. The change in entropy of the surroundings is equal to negative change in enthalpy of the system over the temperature. Very useful equation. Write it down. We're going to use it. Also, we know that the change in entropy of the universe is equal to the change in entropy of the surroundings plus the change in entropy of the system. So this says that when we have a process occurring, the enthalpy of the system changes, and if that's an exothermic process, that means that its delta H is negative. That means this negative would make this a positive number. Temperature is always, this is absolute temperature in Kelvin. So this would be a positive number. The change in entropy would be positive for an exothermic process. Whereas if it's an endothermic process, delta H is positive. This negative makes it a negative, and delta S of the surroundings is negative. The surroundings lose entropy in order for that process to happen. Now, if the surroundings, because the second law tells us that total change of the universe, which is the important thing, it says must be positive for a spontaneous process. We can figure it out. We're going to do this in the next slide. If we know we can figure out the delta H of the system, and we know delta S of the system, we can get delta S of the surroundings from this equation, find delta S of the universe. You'll see. So another way of stating the second law of thermodynamics says that in order for a process to be spontaneous, the change in entropy of the universe must be greater than 0. And when the delta S of the universe is 0 for a process, the system is at equilibrium. That's going to be important later too. All right, so let's look at this, guys. We want to know if this process is spontaneous, non-spontaneous, or at equilibrium at 25 Celsius, given this information. So I'm going to let you guys work on this. This is the dissolving of sodium sulfate into sodium ions and sulfate ions. This is the entropy of the sodium sulfate solid, the entropy of the sodium ion in water, and this is the entropy of the sulfate ion in water. This is the heat of formation, remember from Chem 101, for sodium sulfate solid, sodium ion in water, and sulfate in water. So the process, the idea here, is we can just use one of those first equations here, the AA plus BB equals to CC plus DD thing, to find the change in entropy of our system. Our system here is the reaction. We can find delta S of the reaction by taking the products minus the reactants times their coefficients. That's the delta S of our system. We can get delta H of our system, again, Hess as well, products minus reactants times their coefficients. And then we can use this equation we just saw right here to find from the delta H of the system, delta S of the surroundings. Now we have delta S of the surroundings, delta S of the system, we can get delta S of the universe. So the idea, guys, is when we do all that, if delta S of the universe is positive, this is predicted to be spontaneous at this temperature. If it's negative, it's not. If it's 0, it's at equilibrium. So go ahead and work it out, guys, and come on back when you get an answer. Welcome back. So here we go. First thing is we're going to find delta S of the system, which is the reaction. We're doing all standard conditions here. So again, it's just products, sodium ion, sulfate ion, each times their coefficient. The sodium has 2, minus the reactants. There's just the sodium sulfate there. And we get negative 11.5 joules per Kelvin mole for delta S of the system, the reaction. Getting delta H, change in enthalpy of the system or the reaction. Again, products, this is 2 times negative 240.1, not minus. 2 times negative 240.1 minus, or plus negative 909.3 minus a negative 1385 gives us negative 4.5 kilojoules per mole, or because we have joules here, we want to get joules down here. Or I guess we can convert this to kilojoules if we wanted to, same thing. Anyway, so delta H of our system is negative 4,500 joules per mole. We can use this now in this equation here, our second law, to find delta S of the surroundings. Okay, negative delta H of the system over T. We have delta H, which is negative. We get a positive 15 joules per Kelvin mole for our delta S of the surroundings. Our system is negative 11.5, so delta S of the universe will be delta S of the surroundings, 15 joules per Kelvin mole, plus delta S of the system, negative 11.5, gives us a positive about 3.6 joules per Kelvin mole. Hey, that's a positive change in entropy for the universe, which tells us this process is spontaneous, even though in this case this is an exothermic process, but the entropy is actually decreasing in this case. Now we can do something else with this. So same Same reaction, dissolution of sodium sulfate, same numbers and everything like that. So we can use the numbers we just got. Now the question becomes, at what temperature will this reaction go from being spontaneous to being non-spontaneous? So we found at 25 Celsius what the change in entropy of the universe is. Now, let's see what temperature will make this just delta S of the universe be zero, because once we go past that temperature, now it starts to become negative and this will become non-spontaneous. So basically what we're going to do, guys, is we're going to use this equation right here, solve it for T, right? Where we're going to use the idea that when delta S of the universe is zero, delta S of the surroundings is going to be the opposite sign but the same magnitude of delta S of the system. So, we're going to plug in here, our 11.5 basically, and see what temperature that corresponds to. Watch, you'll see. So go ahead and plug that in real quick, get your answer. Come on back when you get your answer. Welcome back, guys. So here we go. This is what I was trying to say a minute ago. We know that delta S of our system is negative 11.5, and we know that delta H of reaction is negative 4,500 joules per mole. The point at which this switches from being spontaneous to non-spontaneous is the point at which delta S in the universe goes from being positive to negative. We know that at 25 Celsius, 298 Kelvin, this was positive 3.6 joules per Kelvin mole or something like that. So at what point does this become zero and then further become negative? Well, the point at which delta S of the surroundings is negative delta S of the system. Well, delta S of the system doesn't change. That's negative 11.5 joules per Kelvin mole. So when delta S of the surroundings then is positive 11.5 joules per Kelvin mole, that's our inflection point. That's when we go from being positive to negative. So if we rearrange this equation for the temperature, plug in delta S of the surroundings as being positive 11.5 joules per Kelvin mole, put our same delta H up here, solve this, we see that temperature is 390 Kelvin. So at 298, 25 Celsius, this happened spontaneously, but as we increase the temperature, it went from being spontaneous dissolving sodium sulfate to non-spontaneous. And actually, if you look at a solubility curve for sodium sulfate, there's some complicated stuff going on there, but you look at this portion right up here, you'll see that at least qualitatively this agrees. This is one of the few substances where its solubility decreases with temperature. Most ionic compounds' solubilities increase with temperature. This one actually decreases, and we see this going from 298 to 390 Kelvin. We go from spontaneous to non-spontaneously dissolving. And finally, guys, the third law of thermodynamics. What it says is the entropy of a perfect crystalline substance at 0 Celsius, so an absolute zero, is 0 joules per Kelvin. And this actually should be, the units are joules per Kelvin. Watch, let me just change this real quick. So what this does for us is, even though we can't actually achieve absolute zero, this gives us a reference point. So what that means is you can look up in a table the entropy of a substance. That's different. If you remember back to Chem 101 when we talked about enthalpy, LH, delta H, you can't look up the enthalpy of any substance. We don't have a reference point. All you can do is look up the change in enthalpy of a substance, right? We have a reference point, but we can only look up the change in enthalpy. Whereas here, you actually look up the entropy. That's the third law of thermodynamics. And that's all there is to spontaneity and entropy, guys.